Welcome, everyone. Today, we are diving into the strategic implementation of blue-green deployments. Our focus is on achieving zero-downtime releases on Azure Kubernetes Service, or AKS, utilizing Istio Service Mesh for sophisticated traffic management. Looking at the diagram, you will see two identical environments. The blue route on the left represents our current live production environment, which is actively handling all user requests. On the right, we have the green route, which serves as our staging environment where the new version of the application is deployed and tested. The core of this strategy lies in the Istio Service Mesh, which acts as the intelligent gateway between the users and these environments. As highlighted by the configuration snippet at the bottom, we begin with an initial traffic split where 100% of the traffic is routed to the blue environment. This allows for the risk-free deployment and validation of the new version within the green environment. Once the new release is verified, we can instantaneously shift traffic from blue to green. This method provides a robust safety net, enabling us to roll back just as quickly if any issues arise, thereby ensuring a seamless experience for our end users with absolutely no downtime. Thank you.
Modern software development is driven by the velocity mandate. To maintain a competitive edge, continuous delivery is essential, often requiring teams to ship code multiple times every single day. However, this high frequency creates a significant challenge known as the downtime penalty. Traditional rolling deployments carry inherent risks of service interruption and often lead to slow, painful rollback processes when issues arise. To reconcile these competing priorities, we utilize strategic traffic steering at the network layer. By managing traffic flow independently of the application itself, we can effectively mitigate application-level risks, allowing for high-velocity deployments while ensuring maximum system stability and uptime. When evaluating Kubernetes deployment strategies, we consider three primary approaches: rolling, canary, and blue-green. The rolling strategy serves as the default, offering a gradual replacement of pods to achieve zero downtime. However, it is important to note that this method can be slow to roll back if errors occur. The canary strategy provides a progressive, metrics-driven testing environment by routing a small subset of real traffic to the new version. This allows for validation before a full-scale release. Finally, the blue-green strategy utilizes an instant network switch between two identical environments. Although it requires double the resources, it provides an immediate safety net, allowing for an instantaneous return to the previous version if necessary. The core concept of parallel production environments is illustrated here through the blue-green deployment strategy. On the left, the blue environment is active, handling all live user traffic and representing the current stable version of the application. Simultaneously, we maintain a green environment, as shown on the right. This environment is currently inactive for general users, providing an isolated space for rigorous testing with dedicated traffic, completely separate from the production load. By utilizing these parallel environments, we effectively decouple deployment from release. Once the new version in the green environment is fully verified, traffic is switched instantly at the network layer. This approach bypasses the application layer entirely, ensuring a seamless transition for users and allowing for an immediate rollback to the blue environment should any issues arise. Decoupling deployment from release is a fundamental architectural shift that allows teams to move faster with less risk. By leveraging Azure AKS, we establish a robust foundation of elastic compute and managed infrastructure, effectively offloading the operational burden of the underlying cloud resources. On top of this, Kubernetes provides the essential container orchestration and pod lifecycle management needed to maintain application health at scale. However, the true power of this model comes from the Istio Service Mesh. Istio grants us the ability to perform advanced traffic steering and instant routing. This means we can deploy a new version of our service to the cluster without immediately exposing it to users. By separating the technical act of deployment from the business decision of release, we gain the flexibility to perform granular testing in production and execute seamless, zero-downtime rollouts. This network topology illustrates the end-to-end traffic flow within a service mesh deployment. The journey begins with external users accessing the application via Azure Front Door or an application gateway, which provides essential edge security and global load balancing. From there, requests are directed to the Istio Ingress Gateway, which serves as the primary entry point into the internal service mesh. Once inside the mesh, Istio Virtual Service Routing handles the sophisticated logic required to distribute traffic.
This specific configuration facilitates a blue-green deployment strategy, where the virtual service can dynamically shift traffic between the existing blue pods and the newly deployed green pods. This architecture ensures high availability and enables seamless, zero-downtime updates by providing granular control over how and when users are transitioned to new versions of a service.
We are now looking at the preparation of the parallel environment through stages T0 and T1 of the deployment process. In stage T0, our primary production environment, represented by the blue block, is live and actively handling all incoming traffic. As we transition to stage T1, we initiate the deployment of the green environment, which contains the updated version of our application. A key advantage here is that stage T1 utilizes the native elasticity of AKS to provision these new resources. This allows the new version to be deployed side by side with the current one, ensuring that the provisioning process does not impact the existing active pods or the stability of the live traffic flow. Moving into stage T2, our objective is to validate the green release within the actual production environment. As shown in the diagram, the Istio ingress gateway is configured to use header-based routing. This allows us to maintain the existing production traffic on the stable blue pods while simultaneously directing specific requests to the new green pods. By including a custom header, such as x-test-routing-green, internal teams can execute dark launches. This provides a critical opportunity to validate the new version against production databases and infrastructure under real-world conditions, all without affecting live users. This controlled testing phase is essential for ensuring the integrity of the release before it becomes the primary production environment. Moving into the final phases of our deployment process, we execute the atomic traffic cutover across stages T3 and T4. In stage T3, known as the instant cutover, all production traffic is redirected from the legacy blue environment to the new green environment in one atomic action. While traffic is no longer hitting the blue environment, it is intentionally kept online as a standby to ensure an immediate rollback path if any unforeseen issues arise. Once we have completed a period of prolonged health validation in stage T3 and confirmed the stability of the new environment, we move to stage T4, decommission blue. In this final stage, the original blue resources are destroyed to eliminate unnecessary compute costs, concluding the deployment lifecycle with a verified, stable release. To translate a blue-green cutover into Istio configuration, we rely on two core resources, the destination rule and the virtual service. On the left, the destination rule defines the available service versions as subsets. In this example, the blue subset targets version v1, while the green subset targets version v2. On the right, the virtual service manages the actual traffic distribution between these subsets. By setting the weight for the blue subset to 0 and the weight for the green subset to 100, we effectively shift all incoming traffic to the green environment. This declarative approach provides a precise and controlled method for executing the final cutover from version v1 to v2. To guarantee instant rollback capability, we maintain the blue environment as a warm standby, while the green environment is live. Because the blue environment remains fully provisioned and synchronized, our time to recovery is reduced to mere seconds. If an issue is detected in the live environment, a rollback is executed as a simple, instant network configuration change. This approach eliminates the slow pod recreation process, ensuring that we can revert to a stable state almost immediately without service interruption. Managing the stateful dilemma of database migrations requires a strategic approach to ensure zero downtime and data integrity. In a blue-green deployment model, we navigate this by following a specific three-step process. First, we modify the database schema by adding new columns. It is crucial that these changes are backward compatible, allowing the existing blue environment pods to continue functioning without interruption while the schema evolves. Second, we deploy the green environment. These new pods are configured to read from the updated schema, leveraging the newly added columns. During this phase, both environments can coexist, interacting with the same database. Finally, once the green environment is verified as stable, we decommission the blue environment pods and perform a final cleanup by removing any legacy columns that are no longer required. This phased approach minimizes risk and ensures a seamless transition between application versions. Ensuring graceful proxy termination is essential for maintaining service reliability during pod lifecycle events. The process begins by utilizing a Kubernetes pre-stop hook, such as a 10-second sleep, which provides a necessary buffer for endpoint propagation across the cluster. This ensures that no new requests are routed to a pod that is already scheduled for termination. Once the traffic switch is initiated, the Istio termination drain duration setting takes over, defining the specific period the proxy waits to drain existing connections. This stage is critical for allowing in-flight requests to complete successfully, rather than being abruptly cut off. To finalize the sequence, we employ the exit on zero active connections environment variable. This optimizes the native cleanup process by allowing the proxy to shut down immediately once the last active connection is closed, rather than idling for the remainder of a fixed timeout. This integrated approach ensures both a seamless user experience and efficient resource management.
When architecting Azure CNI's subnet IP planning, we face a fundamental trade-off illustrated by this scale. On one side, achieving zero downtime and instant rollback, typically through blue-green deployment strategies, provides significant operational stability. On the other, this approach necessitates a temporary twofold increase in both compute resources and IP address demand. To ensure your subnet is sized correctly for these requirements, utilize the planning formula shown. Total IPs are calculated by multiplying the number of nodes by the maximum pods per node, then adding the total nodes and an appropriate buffer. Finally, to manage cloud expenditures effectively, prompt decommissioning of the legacy environment is critical once the transition to the new stage is complete. To maintain a high standard of operational excellence, we focus on several key best practices. First, we automate the application lifecycle by utilizing progressive delivery controllers such as Argo rollouts or Flagger, which allows for controlled and low-risk releases. Next, it is imperative to enforce the use of immutable image tags. This ensures that our deployments are deterministic, providing consistency across different environments. In terms of visibility, we establish strict observability metrics using Azure Managed Prometheus and Grafana to proactively monitor system health and performance. Finally, we prioritize security during service updates by ensuring secure MTLS transitions, specifically using Istio Pure Authentication during cutovers to protect communication between services.